All right, so we are continuing our derivation of the D3h character table. In the last video, what we did was we were able to figure out that there were 12 symmetry operations, and we grouped those into 6 classes. So we can now write the skeleton structure of our character table. By convention, we always put the identity class first. We had a 2C3 class, put your principal rotation class second. You don't have to do it this way, but if you just want it to match with other character tables that are in the literature, you're going to do it this way. Then we had our n perpendicular C2s, where n equals 3 because we're a D3H point group. So, and then we have a sigma H class, 1 sigma H. We had the 2S3, remember that was the S3 1 times and the S3 5 times. And then we had the 3 sigma Vs. And one of our character table rules states that basically these have to be square character tables. That is, if we have the number of classes has to be equal to the number of irreducible representations. We have 6 classes here, so that means we're going to have 6 irreducible representations. And I don't know what these vectors are yet, so I just give them generic terms that use the Greek letter gamma and just call them gamma 1 through 6. Later on, once we know what the values of the irreducible representations are, we'll be able to assign them Mulliken symbols, which are, more specific labels that chemists like to use because it gives some information about the symmetry properties of the irreducible representation because it embodies some of that information. All right, and so we know that gamma 1 first irreducible representation for any character table is equal to 1s across the board. It's totally symmetric representation. And the next thing we want to do is just test functions. So we start with linear functions. Always start with z first. That's going to almost always give you the simplest answer because z is defined as being coincident with your principal rotation axis. So your principal rotation axis here is a C3. So we're going to be remembering that wrapping around this z pole is going to be our C3 operation, also our C3 too, but we just need to think about the C3. So we're asking the question, hey, what happens to the z vector in all these different classes? And we only have to choose one symmetry operation in each class. So for 2C3, we could do C3 or C32. Those are the 2 operations in that class, but we'll just do C3. And so we're going to think about how this z vector, because we're testing the z function. This is the pictorial representation of the z function, how the z vector transforms. So first we have the identity operation and then identity class. Well, identity takes anything and goes to itself. So z goes to z. And so we can now write mathematically a 1-by-1 matrix that explains this transformation of z going to z. And what the character table is it's a list of the traces or the characters of each matrix that explain the transformation in question. So this is a 1-by-1 matrix. We take the trace of that. It's just a sum across the main diagonals. Well, there's only one element in it, so it's just 1. So we write that chi, the character or the trace of the identity operation, is equal to 1. And so we're going to have a 1 here. All right, let's do for C3. Again, we can do the C3 operation or the C3-2 operation. Those are both in this 2C3 class. And what does z go to? Well, we're doing a 120-degree rotation wrapping around the z vector. So we got the z vector and we rotate it 120 degrees. My finger's still pointing up when I rotate 120 degrees. And what matters is what direction this vector is pointing. So z goes to z. And again, we're going to have this 1-by-1 matrix. And we can say that the trace of this matrix or the character of this matrix is 1. So chi, or the character of the trace of C3 operation is 1. So we have a 1 here. What about a C2 prime? Now there's 3 different C2 primes. We're going to define one of these C2 primes as being perpendicular to the x-axis. That's usually what you want to do when deriving the character tables. It'll make things the simplest for you. And by convention, it's what others do as well. Anyway, we have a 180-degree rotation. We're spinning the everything like this, right? So this z-axis that's pointing up, this z vector is pointing up, is going to get spun 180 degrees and go down. And so z went to the negative of itself. So z went to negative z. And so now the 1 by 1 matrix that explains z going to negative z is actually -1. And so the trace of that matrix is -1. So chi, the character of C2 prime, equals -1. And so we can put a -1 up here. Sigma h. Sigma h is a horizontal mirror plane. And a horizontal mirror plane is horizontal with respect to the principal rotation axis. So the principal rotation axis, remember, is in the z direction. So our horizontal mirror plane is going to be in the xy plane. And so what that does is this z vector is above that, lies above that mirror plane. And so it's going to look at itself below the mirror plane. It's going to get reflected to below the mirror plane. So again here, z went to negative z. And so we're going to get a -1 here on the trace of our matrix. And so chi of our sigma h operation is going to be -1. Our S3 operation, well, our S3 operation, remember, is our C3 operation followed by a sigma h. We figured out that the C3 operation didn't do anything, it just took z to z. And our sigma h operation took z to negative z. So overall, this is going to take, since the first part of this didn't do anything, it's just going to be like a sigma h. So z is going to go to negative z, and our trace of the matrix again is going to be -1. So we put that up here. Sigma v. Sigma v is a vertical mirror plane. We have 3 of them, and they contain the z-axis. They all contain that principal rotation axis. So if a vector is in a mirror plane, it can't see itself in the mirror plane, it's just in it, so nothing happens. So for the sigma v operation, z goes to z. So we have a value of 1 here. And so chi of sigma v equals 1. So you can see we derived a new reducible representation using the z function that was different than gamma 1. And it got us an answer here, which is good. So that's the nice way to get started. And so we're going to carry on and do the same thing here. But now instead of testing the z vector, the natural thing next to do is test x or y. You can do either. We can just, I usually just start with x and see what happens from there. So we're imagining now an x vector. And I'll write x here. We're hoping it gives us something unique compared to gamma 1 and gamma 2. And you'll see that it indeed does. So we just march along here, just like we did with z, and do the same sort of business. So identity operation. Identity operation takes anything to itself, so that's not very interesting. So x is going to go to x. Now let's do the C3. C3, that's a 120-degree rotation. That's going to take x to about here, right? It's going to spin past the y, that'll be 90 degrees to about there. That is going into some linear combination of x and y. And so we need to use the rotation matrix, the 2x2 rotation matrix. This comes from trigonometry. And it basically says that you spin cosine theta here for this first, there's going to be theta values for all 4 elements of this 2x2 matrix, and you're going to rotate by, theta is going to be equal to 2 pi over n. We're doing an n equals 3, so it's going to be cosine 2 pi over 3, or 240 degrees. Negatives to sine 2 pi over 3. I have this memorized. Your instructor might give this to you, or you know, if they're really wanting to prove a point, they might make you derive this. But this is the rotation matrix, arbitrary rotation matrix, 2 pi over n. Here we plugged in 3. What this tells us is that x cannot be defined just in terms of x or negative x, but it embodies also y. And so another way of saying that is x and y transform together, okay? So what we would do here is take the trace of this matrix, okay? And I guess I should write my C3 up here. We would take the trace of this matrix, which is just cosine 2 pi over 3. Cosine 2 pi over 3 is negative 1/2, okay? And so what we end up getting is, I'll just write that out, cosine 2 pi over 3 is negative 1/2. So the trace of our matrix is 2 times that, it's negative 1/2 plus negative 1/2, which is equal to negative 1. So we actually get a value of negative 1 here, something unique already. What this tells us, though, is because x and y transform together, we have to treat them as 2 by 2 matrices. So x goes to x, y goes to y. So really for identity, we need the identity matrix explaining how x, y goes into x, y. So we don't get a value of 1 there, we get a value of 2, because the trace of this identity matrix is equal to 2. 1 plus 1. Okay, we have these 3 perpendicular C2s that we can think about. Last time we said that we're going to define our perpendicular C2 as being, one of them, as being coincident with the x-axis. So if we're rotating 180 degrees that way, and this vector is coming towards us, it's still going to be pointing towards us there. So x for C2 prime is going to go to x. Now, what about a y vector? We know now that we have to consider the x and y together. Well, the y vector is going to go into the negative itself because it was over here and we're spinning this way on the x, so it's going to go to the negative of itself. Okay, and so y goes to negative y. And so the 2 by 2 matrix that explains that transformation is 1, negative 1 with zeros on the off diagonal. That takes you to x, negative y. You take the trace of that matrix, and we're going to get that the chi of C2, the character of C2 operation, is equal to 1, positive 1, plus negative 1, which is equal to 0. So we can put a 0 here. All right, we'll just keep moving along. What about the sigma h operation, the sigma h class? Well, remember the sigma h is in the xy plane. So it contains both the x and y vectors. If the vectors are in a mirror plane, they don't do anything. So x is going to go to x, y is going to go to y. And so you're going to end up with the identity matrix. And so the trace of that matrix, again, is equal to 2. A way of writing that is chi, the character or trace of the matrix, is 1 plus 1, which is equal to 2. So we get a 2 here. S3, remember the S3 we just said was a C3 followed by sigma h. Sigma h didn't do anything to x or y. So effectively, this is the same as C3, right? And so we figured out that that was negative 1. So that's just a very fast way of knowing, hey, it's going to be the same as C3 in this case. So it's going to be negative 1. And then the sigma v's. Sigma v's are more of a one that we have to think about here. If you remember our discussion in the previous video, we found that there's a perpendicular C2. Perpendicular C2s could go through any of these vertices, but we defined here that one of our perpendicular C2s is coincident with the x-axis, and the vertical mirror planes overlap with those C2s. So effectively what that means is that our vertical mirror plane is going to be in this XZ plane. And so if it's in the XZ plane, that means that X is going to go to X because it's in the mirror plane, but Y is to the right of the mirror plane, so it's going to see itself on the left of the mirror plane, and that means that Y is going to go to the negative of itself. And so our 2 by 2 matrix ends up, that describes this transformation equals 1, negative 1, 0, 0. And so it goes like that. So we get a trace or a character of the matrix being 1 plus negative 1, which is equal to 0. So we figured out the gamma 3. So at this point, we've done the linear functions. We've tested all the linear functions that there are, right? X, Y, and Z. And so what else can we do? The logical thing here is to test quadratics, okay? And there's several different quadratics that you can test, and so to show you an example of how this can work, some of these you have to sort of derive using math, and this example we're not actually going to do that. It turns out that won't help us for this case, but in a lot of my other character derivations we do that extensively. In this case, so we're just going to think about some of the symmetry of the d orbitals. So one of the symmetries of the d orbitals is z squared, or at least a shorthand for z squared. Z squared ends up having similar symmetry as 2z squared minus x squared minus y squared, but for almost all point groups. So if we think about z squared, what would that do? Well, what you can do is you can just think about z and what happens if you square all these components. We have ones or negative ones, so if you square all those, you're going to get positive ones across the board. And so you're going to get that z squared transforms as gamma 1. That, of course, doesn't help us derive the character table, but it gives you an idea of how this works. So what if we multiply z times x comma y? That's going to get you xz, yz, right? And it tells, those are d orbital symmetries as well. And it tells you that, well, hey, z transformed by itself, and if I'm multiplying by xy, I'm going to get the xz and yz transformed together, just like xy did. And then we just multiply these. So we're just multiplying gamma 2 and gamma 3. 1 times 2 is 2. 1 times negative 1 is negative 1. 0, negative 2, and a 1, and a 0. And very quickly, we just derived a new irreducible representation with a dimensionality of 2, because 2 functions transform with it. Okay, and so another thing that you can test in addition to quadratics is rotation vectors, but probably a good, so like RZ, but a good thing to do at this point is to see what the dimensionalities of these two last components are. We could have actually done this in the beginning, but so what are the values of A and B here? And one of these character table rules that we have is that the sum of the squares of the dimensionalities, so the characters under the identity class, so that's the sum of the squares of the dimensionalities, 1 squared plus 2, 1 squared plus 2 squared plus 2 squared plus our unknown squared, a squared plus b squared, has to equal to the order of the point group, which is the number of symmetry operations, total number of symmetry operations in the class, which we know is in the point group, which we know is actually equal to 12. Is equal to 1 plus 2 plus 3 plus 1 plus 2 plus 3. And these values here under the dimensionality have to be integers. They have to be whole numbers, 1, 2, 3, 4, 5. Almost always they're 1s and 2s, except in the really symmetric point groups. So if you look at this, 1 squared plus 1 squared plus 2 squared plus 2 squared, that's equal to 10. So we have 10 plus a squared plus b squared equals 12. Tells us that a and b both have to be equal to 1. And that'll just kind of help us think about, what these values should be. So that's sort of a good thing to do. You can do it earlier on and actually figure out, hey, all these are 1, 1, 2, 2, 1, 1. That can also help you. Okay? Or you can do it later. So let's think about the RZ. An RZ function, how does that transform? RZ function is just a rotation vector. It's actually this vector wrapping around the z-axis. So identity, of course, is going to take RZ to RZ. So we have a 1 there. What about a C3? A C3, how does RZ transform? Well, we have this vector, and now we rotated it around the z 120 degrees. That's what a C3 is. And so the tail and the head are going to move by 120 degrees. But this vector is defined by the position, by the directionality in which the rotation is occurring. So this direction, right, is still going counterclockwise. And so RZ went to RZ here, and we know that then we have a trace of the matrix is going to be equal to 1, right? Because we have this 1 by 1 matrix. So if RZ goes to RZ, we're going to get 1. If RZ goes to negative RZ, we're going to get negative 1. Those are our only options here because we're a one-dimensional system. Okay, so C2 prime. C2 prime, we know that we define one of our C2 primes as being coincident with the x-axis. So we're doing a 180-degree rotation this way. We're taking that rotation vector, we're flipping it like this. So in other words, now this rotation vector, we're doing a rotation on it, C2 on it, right? We're doing 180 degrees like that. Well, that's going to cause it to flip, and so the head and the tail are going to switch positions. Well, we went from counterclockwise to clockwise, and so that is RZ going to negative RZ. That's going to get us a negative 1. Sigma H is our next one. Sigma H, remember, is right here in the xy plane. So this vector is how we drew it. It's kind of above this plane, and now it's going to reflect below that plane. The head and tail are still going to see themselves in the same relative positions, so we're still going in the same directions. So the direction hasn't changed, and we get a value of 1. S3. S3 is, remember, C3 followed by sigma H. We just figured out a sigma H didn't do anything, and we also knew from earlier C3 didn't do anything. Both of those just took Z to Z. So S3 is also going to take, sorry, RZ to RZ. So S3 is also going to take RZ to RZ, so we're going to get that value of 1. Last one is sigma V. Sigma V is perpendicular to the sigma H. One of them cuts through here, contains that Z plane. You can see it's cutting through that rotation vector. So if we have a mirror plane, very similar to the C2, that's cutting through the rotation vector, the head and tail are going to see each other in the mirror, and you're going to end up getting a flip of the two, and that's going to change the direction of your rotation. You went from anti-clockwise to clockwise, so you get a negative 1 here. RZ went to negative 1. So that was a fast way that we're able to derive another irreducible representation. At this point, we only have one more left, and so the easiest thing to do here is just to try to come up with values. You know it's going to be 1s and negative 1s because you have a dimensionality of 1 here, and you know you need to be orthogonal. That's one of our character table rules. So gamma 6 is what we're trying to figure out. That has to be orthogonal with gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. All of them have to be orthogonal to each other. We could check that for the ones that were derived, and it would be true. But orthogonality means that the dot product has to be equal to 0, right? And so what you can see here is that in all these cases where you had 1s and negative 1s, so gamma 2 and gamma 5, you have 3 negative 1s, or here you have 2 negative 1s. And the way that works is that because this dot product is weighted by the number of symmetry operations in each class. So here you have 3 negative 1s because it's weighted by a 3, by a 1, and a 2. So what I mean by that is, let's just do an example of why gamma 1 dotted with gamma 2 is actually equal to 0 here. So gamma 1 is ones across the board, right? So when we do the dot product, we're going to have a bunch of ones, 6 ones. And then gamma 2 is when we're multiplying by 1, 1, negative 1, negative 1, negative 1, and 1, just taking that vector. And all these are going to be added up, okay? But then, like I said, we have to wait for the number of symmetry operations in each class. So there's one symmetry operation in the identity class. There's an imaginary 1 in front of this. There's 2 symmetry operations in this 2C3 class, so I multiply by 2. There's 3 in 3C2 prime class, 1 in the sigma H, 2 in the S3, 3 in the sigma phi. So that's how this all works, and you end up adding this up and you get 0. Basically, 1 cancels out with negative 1, negative 3 cancels out with positive 3, and negative 2 cancels out with positive 2. So you get 0. That's just a check. Again, if we checked all of these, they're going to be 0. But we can use this principle to help us derive gamma 6. And what I'm saying is gamma 6 dotted with gamma 1 has to be equal to 0. And so you can see why here, how this worked is the weighting we had with gamma 2, we had the 3 negative 1s be next to a 3, a 1, and a 2. Well, that adds up to 6. So we got basically negative 6. And then our positive ones were 3, 2, and 1 there. Here, we only had 2 negative 1s, but it still added up to 6 because we had negative 1s on the 3 and the 3. So the other combination that we don't have is the three negative 1s going on this 1, this 2, and this 3. That's the only other combination we don't have. And so that is a good guess. And then these are going to be positive ones. So again, you have 3 positive ones, 1, 2, 3 adds up to 6, a positive 6, negative 1, negative 1, negative 1. That adds up to a negative 6, 1, 2, and 3. And that ends up being our answers. You can check this, but gamma 6 will be orthogonal with all other components. So gamma 6 will be orthogonal with gamma 5, gamma 4, gamma 3, gamma 2, gamma 1. Again, you have to weight it with the number of symmetry operations in each class. And so our last step here is, now that we've come up with all the different irreducible representations, all 6, we can erase these gamma 1s, gamma 2s, gamma 3s, gamma 4s, gamma 5s, gamma 6, and put in the appropriate Mulliken symbols. So the way that we do this is that for, if we have a dimensionality of 2, okay, dimensionality is a character under the identity operation, you're going to use a Mulliken symbol of E. So these two vectors have values of 2 here, so I put E. This E is a Mulliken symbol E, not to be confused with the identity class E. Same nomenclature means different things. If you have a value of 1 under E here, the identity, you're going to be an A or a B. Okay, that's the Mulliken symbol that you're going to use. You're going to use an A if you have a value of 1 underneath the principal rotation axis, which is C3. You're going to use a B if you have a value of negative 1. You can see that here we have a value of 1, so we use an A. Here we have a value of 1, we use an A. Here we have a value of 1, we use an A. And here we have a value of 1, we use an A. All these are A's. Now we have 4 A Mulliken symbols and 2 E Mulliken symbols, so that's not very useful. We want to delineate between these even more. So with these DH point groups, when you have a sigma H, you're going to use primes. And primes tell you primes and double primes. You use prime if you're symmetric with the principal, with the sigma H, and you use double primes if you're anti-symmetric with the sigma H. So if you have a positive value here, you're going to be a prime. If you have a negative value here under sigma H, you use a double prime. So we have a positive value there, we're going to use E prime. Here you have a negative value, and you use a double prime. And here you have a positive value, so you use a prime. Here you have a negative value, so you're going to use a negative prime. So now our E prime and E double primes are two-dimensional vectors, are differentiated from one another. But we still have 2 A primes and 2 A double primes, so we have to differentiate between those. And we're going to do that with subscripts 1 or 2. So just Mulliken symbol rules. And subscripts 1 or 2 correspond to the perpendicular C2s. If you have a positive value here, if you're symmetric, you use a 1. If you have a negative value, you use a 2. So I have a 2 here because I have a negative value. I have a negative value here. I'm going to use a 2. And I have a positive value here. Use a 1. So now we've differentiated between all of our different 6 Mulliken symbols, our irreducible representations using the Mulliken symbols, so it's easy to talk to chemists about this. And this is the complete derivation of the D3h character table. You can look this up online and you'll get something very similar. You can see the ordering of these rows is different than what we came up with. It's arbitrary, right? Even the ordering of these columns is arbitrary. I put it the same way because I knew how character tables do it. But all this is arbitrary, so you can scramble these in any way, and it's fine, right? Mathematically, it's the same thing. We derived these quadratic functions. You can see some other quadratics that we didn't look at. Of course, the cubics we didn't look at. We didn't need those. Some of the more complicated character tables in my other derivation videos, we do use these extensively. But you can see A1 double prime, which we derived there at the end there, doesn't transform as any of these functions. There's more complicated functions that aren't really chemically useful that it transforms as. But for that reason, it's best to just use the other character table rules and derive that last, like we used the principal orthogonality to tease that out. So there you go. Hope you enjoyed this derivation.